Today we're going to look at energy in terms of stoichiometry and how we would involve heats of reaction in a stoichiometry type problem. Now, when we have heat of reaction, remember a couple of things. One, it can be an exothermic reaction, meaning heat is given off. And an example of that would be this reaction. And notice where the heat term is. If it is an exothermic reaction, the heat term is always going to be on the right-hand side of the arrow, the right-hand side or product side of the equation. And just as it says up here, that value is going to be negative. So a negative delta H, negative heat of reaction, the heat term is on the right, exothermic. If it's endothermic, exactly the opposite. The heat term is going to be on the left-hand side of the equation, and it's going to be a positive value because heat is being absorbed in the chemical reaction. When the heat term is shown in the chemical reaction, it's called not just a chemical equation, it's called a thermochemical equation because it shows both the chemicals that are involved and the heat that's involved. So, an example. How much energy is required to decompose 500 grams of calcium carbonate? The heat of the reaction for the calcium carbonate reaction is, and we look up here and we see that the value's right here, and what I want you to put here is that the heat of reaction is a positive 176 kilojoules. And technically when we see this, we always talk about it being per mole reaction, per mole Rxn, meaning that's how much heat is involved per mole of the reaction that is written, the reaction as it is written. So if we want to solve this problem asking us about how much energy we need to decompose 500 grams of this calcium carbonate, the first thing we need to do is to write the equation. And label it just like we always have. So it told us we had 500 grams of calcium carbonate, and it wants to know how much energy. So our heat term, our energy term here is going to be our unknown. So we don't need any of this other information. Our ratio is going to be like, I guess you could call it an energy ratio because we're going to treat this number value kind of like a substance in a chemical reaction. So what this says is that if we have 1 mole of calcium carbonate, we would have 176 kilojoules involved. So that's going to be our mole ratio or energy ratio, if you will. So if there were a 2 up here, if there were a 2 here to balance this, then I would have done just like I always do in stoichiometry problems, and I would have put a 2 here in that position in our ratio. But it's not, so I'm going to erase that off before it causes confusion, and we're going to go on with the problem. We're going to start the problem with what we know. We know we've got this much calcium. We're trying to find the energy. So 500 grams of calcium carbonate. We can't use that ratio yet because we don't know how many moles of calcium carbonate we have. We need it to be in moles first, as always. So we look at the molar mass of calcium carbonate, 1 calcium, 1 carbon, and 3 oxygens, and we get that there are 100.09 grams of calcium carbonate per mole of calcium carbonate. And now that we've got it in moles, now we can use our ratio. And it looks like we need for moles of calcium carbonate to be on the bottom so that it will cancel or reduce to 1. So according to our ratio up there, it's 1 mole of calcium carbonate for every 176 kilojoules. And moles of calcium carbonate cancel. I'm left with kilojoules, which is what I wanted, the amount of energy. And when I multiply and divide this out, I end up with 879.21 And when I get this to, looks like we're going to need 3 sig figs because of this value. This one has 4, this one has 5. So the least number is 3 sig figs. So correct scientific notation in sig figs, we get 8.79 times 10 to the second kilojoules. Our next problem asks us how many kilocalories or kcals that would be. And the conversion factor is that 1 kcal or kilocalorie is 4.18 kilojoules. So I'm going to start with my value that I just determined. Now remember, we don't want to use a rounded value, so I'm going to go back to my 879.21 kilojoules and convert that to kcals or kilocalories. So there's 4.18 kilojoules for every kilocalorie. Kilojoules cancel. Left with kilocalories, and to 3 sig figs, correct scientific notation, it looks like I have 2.10 times 10 to the second kilocalories. I'm going to go back to my original number of sig figs, which is 3. So there's the answer to that problem. Our next question asks us how many grams of oxygen we need to produce 750 kilojoules of energy. Now, which equation is this using? It's using the one up here that deals with oxygen, which is the carbon plus oxygen yielding CO2. So let's rewrite that equation down here so we have something to label. And in that equation, if you noticed, it said that the value for the heat of reaction was 393.5 kilojoules per mole reaction, but be careful because it shouldn't have a dot there, by the way. It should just be mole RXN. This is an exothermic reaction. The heat term was on the right, so make sure you don't forget that that is going to be a negative value there. So watch for that. So our reaction was carbon plus oxygen yielding CO2 plus 393.5. We never put negatives in chemical equations. The fact that it's on the right-hand side means that it is a negative value. It's exothermic. So labeling what we've been given, we're looking for X grams of oxygen, and we're given 750 kilojoules of energy as our known. So it looks like our mole ratio or energy ratio is going to be that we have 393.5 kilojoules for every 1 mole of oxygen. And again, if there's a coefficient in front of that oxygen or any other substance in the chemical equation, then that would change that mole energy ratio. So starting with what we have underlined in the problem, the 750 kilojoules of energy. We can go straight to the mole energy ratio. Looks like we need kilojoules on bottom, so the 393.5 kilojoules will go on the bottom, the 1 mole of oxygen on top. And now we're at moles of oxygen, but we don't want moles of oxygen. We want grams of oxygen. So we're going to need our molar mass. 2 oxygens add up to 32.00 grams per mole. And when we multiply this out, we get 60.99. And it looks like based on our sig figs, we have 3 sig figs here. We have 4 sig figs here and 4 sig figs here. So it looks like we need 3 sig figs in our final answer. So it becomes 6.10 times 10 to the first grams of oxygen. And those are our energy calculations.